Hi everyone, I'm Cezar, a PhD at the University of Groningen, and today with my supervisor Andrea Capiluppi, we are going to present you our work on using structural and semantic information to identify software components.
Hi, my name is Andrea again. So the intuition behind this work is very simple. So the idea is that you take a software system and you try to sort of apply like a double-pronged approach. The first one is to try to extract some structural information, and the structural information does create some modules and components. So when you start trying to pick up the connectors between very small identities like files or classes, then you create like agglomerates of these classes, and then you can call them modules or components. And then from the structural clustering of these components, then we take each of the components and we try to analyze whether or not in those components there is some sort of homogeneity in terms of cohesion, in terms of similarity, in terms of similarity of scope and similarities of functions. So the first step again is like a structural analysis of the graph, and then try to understand whether or not the identified subclusters belong to each other in a sense. So the technical details are in the next slide.
Okay, so yeah, we start from the source code of the project, and from the source code we extract the dependency graph, where almost each class is a file, let's say, and we have a node, and based on the nodes we have the imports and dependencies, we have the edges between the classes. And then we perform a community extraction on the dependency graph, and the output is a partition of the graph. In parallel with this, we also do the extraction of the embeddings. So for each file, we create a representation, a vectorial representation that we will use in the next step, which is the component semantic analysis, where we align the semantic information with the structural information and measure for different metrics, the cohesion, separation, the correlation between the dependency and the similarity of components, and then the silhouette. So overall is trying to understand how semantically cohesive, separated are the extracted communities. If you want to have a better understanding of the metrics, you can refer to the paper. So how do we do the extraction of the communities? We use two different algorithms that we want to evaluate. The first one is InfoMap, which is an algorithm that works on the optimization of information flow. So communities that, so a community is a set of nodes where information can easily flow inside this community. So how does it work? First, InfoMap creates a random walk in the graph, then encodes this random walk using Huffman coding, and then identifies the communities by performing an optimization on the first set of codes, which gives us the communities. The second algorithm that we use is Leiden. Leiden, on the other side, optimizes modularity, which is a measure of how cohesive and at the same time separated components are. In this case, is structural cohesiveness and separation. Leiden starts by assigning each node to its own community, then starts moving nodes into communities by trying to improve increase the modularity. Then there is a refinement stage where some communities get separated. Then communities are aggregated into, let's say, a giant node, and then the process is repeated until we cannot further increase the modularity. Regarding the extraction of the embeddings, we use three different representations techniques. The first one is TF-IDF, the second one is BERT, and the third one is fast text. And then we apply these three techniques to two different representation of the source code. The first one is the identifiers in the files. And then the second one is the package plus class name. This gives us a higher level view of the code. So here we can have a look at our results. First of all, we can see that the number of communities that have been extracted varies between the two algorithms. In particular, Leiden extracts more communities that have smaller size, while Infomap extracts less communities, therefore they're larger. Here we can have a better view of the space of the communities identified by Leiden and Infomap and their semantic meaning. So on the X and Y axis, we have the semantic space. So if two nodes are close semantically, they will be close also in this space. The color and the label on a point represents the community identified by the corresponding community detection algorithm. So from Infomap, we can see that, as previously mentioned, it extracts communities that are larger. And this also translates in the fact that sometimes it can basically just cover the entire semantic space of the project. While Leiden suffers from this from time to time, as we can see here with some communities. The ones identified with Leidens are more cohesive and are semantically more close to themselves instead of covering the entire space, even if this happens.
Yeah, so as a general sort of conclusions, personally, I was using Infomap before, and I was like sort of, well, the idea was to start to compare the results of Infomap with Leiden. And of course, the difference is that in terms of the size of the communities, the communities of Infomap are larger. But well, in terms of the size, they're not like when you would look at the other results in the paper, they're not completely out of bounds in terms of the Leiden and Infomap. So they're still in the same sort of ballpark sort of size. But yes, Leiden has got the tendency of creating smaller communities and smaller components to the risk of being too expensive to sort of analyze one component made of a couple of classes, for instance. So that is definitely an issue. But on the flip side, Leiden, of course, has got the advantage of having like a better separation in terms of the concepts and the semantics of those components. And of course, when you want to sort of have a trade-off of these characteristics, Infomap, of course, when you want to have like a better better understanding of the cohesion of those components in terms of the semantics, yes, Infomap has got that sort of an edge. And again, in terms of future work, inevitably we need to increase the sample of these applications. And again, in terms of the evaluation of the sample, it's also inevitable to start and think what's actually inside of those components in terms of the concepts, and that cries for a qualitative evaluation. And then there is like the third set of future work, which is actively being worked on by Cezar. Is about the classification of the component. So once we know that a component is clearly separated from another component, can we say something, apply, let's say, a label and say, so that component is definitely a component that does networking stuff, or it does maybe clustering stuff. So we need to apply some labels to clearly classify components that are identified by a clustering algorithm, for instance. And that is the idea of this paper. So thanks a lot for listening. Thanks a lot for making it through, and we will see you at the venue.